Okay, good morning, everyone. So, kumusta naman ang reading break? I hope you guys had a good time to catch up sa mga lessons or just relaxing and uh, getting getting some well-deserved pause from academic stuff. So, tapos pagbalik natin ngayon, ang hirap bumalik sa academic shape, right? So parang ayoko na nga rin bumalik sa semester, but we don't have any choice. But some housekeeping matters first. I hope you already saw the feedback to the problem set problems, at least for PS 1.1 and 1.2. I graded both of them, and for those who had some troubles submitting it in Canvas and had to submit it to me via email, paki-remind lang ako kung hindi ko pa nag-grade yung PS 1.1 and 1.2. I think I graded everything. Baka lang nakalimutan kong i-grade yung sa inyo. So kindly send me a message if you didn't receive your feedback for problem set 1.1 and 1.2. And then your lab instructors were assigned to grade 1.3. So naantay ko pa yung ibang lab instructors to finish grading your work para makapaglabas ng top notchers for the first problem set. But I guess for most of you, makikita nyo na yung standing nyo sa Canvas, so kindly check it out. And then also we have on Canvas, we have, I think, three worksheets that will be due on the 15th. Kasi ngayong reading break, hindi pala ngayong reading break, ngayong week after the reading break, hindi pa rin pala pwedeng magpa-submit. There is a memo from the Office of the Chancellor prohibiting faculty members from requiring any submission this week. So yung deadline ng worksheet 6 is moved to November 15th, which is also the new schedule for worksheet 7. Tas ito yung original schedule for worksheet 8. So don't worry, worksheet 8 might not be due on the 15th. Pero simulan nyo na hopefully yung worksheet 6. Pwede na kayo mag-submit, but the deadline was moved to November 15th. And then worksheet 7, depende kung hanggang saan yung matatapos natin this week. I-move natin accordingly or posibleng ma-move yung deadline for worksheet number 7. Okay? And then for this week, we will start a new chapter in Math 101, which is basically a notion of axiomatic set theory or a discussion about axiomatic set theory. So in the previous chapter, we developed logical tools or tools from logic, which we applied to mathematical statements. Natutunan natin, nagsimula tayo to a recap of propositional calculus, which is the study of the uh, the validity of arguments involving propositions. So propositions, declarative sentences that have a truth value. So tiningnan natin how these propositions make up an argument and how to basically determine whether an argument is valid or not. And when we say validity, this is more of a look at the structure of the argument. We're looking if the conclusion will follow from the premises. And then we took it a notch higher when we talk about predicate calculus. When we talk about predicated statements, wherein we have a term and we have the actual predicate. So ito ay mga statements na nag-apply to certain elements of a domain or a set of objects under consideration. And then usually meron siya mga quantifiers. Tiningnan natin yung different cases on how to prove formal statements or how to prove the validity of formal arguments involving predicated propositions, right? Na may quantifiers pa. And then we applied this into mathematical statements na informally stated. When we say informally, hindi na siya yung symbols na P and Q or P of X and Q of X. Sila na yung English version ng mathematical statements. Tapos nakita natin na all of mathematics, or at least those examples that we have seen, are predicated on some rules of logic. All right? So ngayon, titingnan natin paano to i-apply to a larger mathematical discourse. Kasi medyo contrive yung mga example natin during the first half of the semester when we talk about specific mathematical statements, pero we assume yung mga alam natin from say high school or from elementary, like the basic properties of divisibility, pagiging even, pagiging odd. But if you will recall, we didn't start from scratch. And starting from scratch is a basic axiom in mathematics. So usually in any mathematical discourse, we have this what we call the meta-axiom of ignorance. Kaya siya meta-axiom kasi siya yung parang, siya yung nauna. This goes without saying na in any mathematical discourse, you always start from scratch or almost from scratch. When I say meta-axiom of ignorance, ang ina-assume ko lang ng alam nyo dito sa ating discourse or sa ating discussion ay lahat ng undefined terms, lahat ng terms na na-define, yung mga axioms or statements that were assumed for the sake of what is to follow, and then all proven statements. So outside of that, wala na kayong alam. Yun yung sinasabi ng meta-axiom of ignorance, which might be a blessing in disguise whenever you are studying mathematics. Kaya mapapansin nyo, or when you go to your major courses, you will see that we painstakingly start from scratch all of the discussions. Kahit yung mga basic na definition or mga basic na theorems na probably alam nyo na from Math 36, 37, and 38, or even from high school mathematics, ay dinidefine pa uli or pinuprove pa uli. Kasi nga sa kahit anong mathematical discussion, lagi tayong may meta-axiom of ignorance. So para nalilay out or nalilay down from the very beginning, ano yung mga bagay na assumed na alam nyo na or hindi pa. Okay? So in this discourse, meron siyang fina-follow na certain logical foundation. Parang isa siyang template para sa kahit anong mathematical study or any mathematical field. Yun yung tinatawag na axiomatic method. And for this first session, we will look at the historical development of this axiomatic method. Ano yung mga important developments or important events that led to the development of the axiomatic method that we know today. Okay? So, as the name implies, pag sinabing axiomatic method, syempre magsisimula tayo sa axioms or sa logical axioms. Pero this all began when mathematicians started looking at the body of mathematics as logic. Okay? So, yung mga ancient mathematicians siguro, their main concerns would be for computing things for everyday use, like the early Egyptians when they used or developed their numeration system to answer practical problems like counting their produce or building their great infrastructure, right? So, gumamit sila ng math, pero hindi ganon ka-formal yung discussion nila ng mathematics because they are talking about mathematics for its practical purposes. Pero as the field evolves, probably in the 1600s, I think 16 or 1800s, there's already a quest to put an axiomatic or a certain template for the study of maths. So ito yung tinatawag natin na parang nagkaroon tayo ng reformation in how we look at mathematics. So we are looking or we are trying to build mathematics as a logical system. And yun nga yung pinag-aralan natin sa chapter 1 when we look at methods of proof, how they are applied to mathematical statements and all. And there's a mathematician, Gottfried von Leibniz, who thought about unifying mathematics. Parang isa to sa mga common themes in any field of study. Laging yung mga great proponents of that field of study, be it mathematicians, physicists, or chemists, they always have an ambition to create a single unifying theory for everything. And in mathematics, it's not a different case. So there are several famous mathematicians who wanted to develop a notion of a universal mathematics or a unifying theory for all of mathematics. Isa sa kanila ay si Leibniz. Gusto niya mag-develop ng calculus of reasoning. Kasi during his times, they already started looking at mathematics as a logical study or as a field of logic. Okay, so it then follows that following Leibniz thinking na dapat merong isang universal truth that will govern all of mathematics. So gusto niya tuloy ngayon magkaroon ng isang universal system of logic or language para masystematize yung pagde-develop ng mathematics of everything. But 200 years later, dun pa lang nagkaroon ng formal symbolic logic, and this was published in the Laws of Thought in 1854 by George Boole. So, tinreat niya yung logical discourse as a system, as a mechanical system, na para ba siyang arithmetic, right? At ito yung pinag-aralan natin last time, yung symbols ng mga connectives and so on, how to construct truth tables in order to determine the truth value of compound propositions or the validity of arguments. All of them are due partly to George Boole, who formalized everything. Okay? Tapos, it was then followed by works of Bertrand Russell and Alfred Whitehead when they published Principia Mathematica, which again follows the dream of Leibniz of unifying everything or deriving all mathematics from symbolic laws of thought. Okay? Tapos makikita natin after Bertrand Russell and Alfred North, there's somebody who broke this dream of theirs na sabi niya hindi posibleng makarakterize completely ang mathematics as a logical discourse. Okay, but how did they do this? How did they formalize mathematics as an axiomatic system? Now, this idea is due to David Hilbert, who is one of the proponents of championing or honoring the dream of Leibniz na magkaroon ng calculus of reasoning. So ang ginawa ni David Hilbert, finormalize niya further ang mathematics as a system in which all mathematical truths or theorems could be derived from a few basic assumptions called axioms by applying rules of logic. At ito na nga yung simula ng modern type of mathematics that we now know. Ano ba yung axioms? Well, axioms are basically self-evident truths that need not be proven. Yung mga axioms, ito yung mga statements na hindi natin pinuprove. Ina-assume natin sila to be true for the sake of what is to follow. And this is the very foundation of the mathematical study. Of course, kung isusulat natin siya in a diagram, probably we can summarize any mathematical discourse to start with undefined terms. Okay. Ito yung mga bagay that are very much basic na hindi na siya or walang paraan para ma-define siya logically. For instance, what's an example of an undefined term? An undefined term, for instance, ay set. We say that intuitively, a set is a collection of objects. Okay? So, paano natin i-define yung collection of objects? Kasi ang isang definition, dapat meron siyang dalawang parts. Meron siya dapat genus. So, genus which basically connects it with other known objects, and a differentia which distinguishes it from other similar objects. So pag sinabi nating set, collection siya ng mga objects. But how do we define collection? Pwede mong i-define yung collection basically, or pwede mong sabihin siya ay parang aggregation or para siyang ano pa ba, group of objects. Pero ano yung group of objects? So yung group of objects, ano ba siya? Eventually, if you continue the thought process, babalik ka dun sa term na set. So magiging circular yung reasoning. We cannot provide a specific definition for the set. That's why it is accepted as a undefined term. Another example is a point. Tandaan niyo ba yung sa high school, paano define ang isang point? Having a point, point is a very important term sa geometry kasi siya yung ginagamit para ma-define yung line, right? So we say that a line is composed of infinitely many points. So, pero ano ba yung definition ng point? So basically, a point is an undefined term. Hindi natin siya ma-define in a very formal and specific way. But we need this notion, or we need the notion of a point in order for geometry to progress. Kaya tinatanggap natin siya as an undefined term. And then, of course, if you have your undefined terms, usually these undefined terms are used to provide a definition for other terms or objects in our universe. So magkakaroon tayo ng mga defined terms as well. But after um, we have specified these terms or these objects of our mathematical discourse, papasok na dyan yung axioms. So axioms are basically, these are self-evident truths, statements that need not be proven, and they would serve as the very foundation of our mathematical system. Parang isipin nyo siya na assumption. Sila yung mga assumptions sa isang mathematical discourse. And all theorems, all definitions, all other statements in that mathematical study will follow from the axioms. So after no axioms, manganganak na yan ng mga theorems at iba pa mga results. And that's how important axioms are, because they serve as the basis for the mathematical discourse. So if you're developing a certain mathematical field which is similar to existing ones, um, pwede mo siyang gawin by just changing one of the axioms, right? And if your axioms is independent from the axioms of another mathematical discourse, then the brand of mathematics that you will be developing will be different from other mathematical branches. So, kaya napakahalaga ng axiom. Siya yung nagdidikta kung ano yung magiging itsura ng entire mathematical system. So, let's see, ano pa yung gustong sabihin dito? Okay. All right. So, sa isang ideal axiomatic system, meron tayong mga hinahanap ng mga properties. So, ito yung mga gusto nating properties ng isang axiomatic system, or basically ito dapat yung mga properties na gusto natin sanang makamit ng mga axioms. Una, uh, the mathematical system or the axiomatic system must be finitely describable. Meaning, meron ka lang finite number of basic axioms. So, kung mag-iimbento ka ng isang mathematical discourse, ayaw mo ng napakaraming mga assumptions or napakaraming mga basic statements na hindi pinuprove. So, that's why we want to have a limited number of basic axioms. So, dapat kakaunti yung foundational concepts. Second, of course, it must be consistent. There should be no internal contradictions. So pag sinabi natin consistent, ibig sabihin ng isang axiom ay hindi nagko-contradict sa isa pang axiom. So probably, should I give an example of this right now? Okay, an example would be, halimbawa, sa Euclidean geometry. We will see this later in a more formal sense, but if you remember the fifth postulate of Euclid, tandaan nyo ba yung fifth postulate ni Euclid? Anyone?
No, sir.
Sorry, hindi ko masyadong narinig.
Sir, I don't know, sir.
Okay, yeah, no problem, Victor. Yeah. Yung fifth postulate ni Euclid, sabi niya, on a line passing through a point, there exists a unique parallel line. So kahit sa anong line daw, merong isang parallel line. There is at least one parallel line that exists to that particular line. So pag yun yung ginamit mo na axiom, hindi ka pwedeng magbigay ng axiom na contradictory to that one. So hindi mo pwedeng sabihin na there exists no parallel line. Kasi nga yung unang axiom na dineclare mo ay there will exist at least one parallel line. Pero pag nagdagdag ka pa ng axiom na sabihin mo walang parallel line na nag-exist, then that will be contradictory. So dun pa lang sa pagkaka-define ng axioms, ayaw mong magkaroon ng contradiction sa kanila. And it is not limited to the contradictions within the axioms or among the axioms, but also ayaw mo magkaroon ng contradictions mula dun sa mga implications ng mga axioms na yon. Sasabi nga natin yung mathematical discussion, meron siyang terms, tapos meron siyang axioms. So sa mga axioms, nakaka-imbento ka ng mga theorems. Now, ayaw mo magkaroon ng dalawang theorem na madiderive mo from the same set of axioms that are contradictory to each other. So kaya gusto natin dapat consistent yung mathematical discourse. The third one is that it should be complete. So complete siya, ibig sabihin dapat yung mga mula dun sa basic axioms, dapat kailangan nating ma-derive lahat ng mga mathematical statements. So, ibig sabihin, the basic axiom should allow analysis of every possible situation, meaning kung meron akong isang statement about my terms, then I should be able to determine whether that statement is true or not using the axioms. All right? So, isipin nyo lang siya na halimbawa sa geometry, meron akong mga postulates na binigay. Kung complete yung geometry na inimbento ko, ibig sabihin, pag nagbigay ako ng isang statement, kaya ko siyang ma-prove to be true or to be not true using the declared axioms. So parang ibig sabihin, lahat dapat ng problems may solution kung complete yung axiomatic system. Alright? So every statement must be proven to be true or not, or must be provable to be true or false. So yun yung ibig sabihin ng completeness. And then number 4, the axioms must be independent. Walang axiom ang dapat kayang ma-prove mula sa isa't isa. Okay? So if you declared 5 axioms, okay? So kung may 5 kang axioms, dapat hindi mo pwedeng ma-prove si axiom number 5 mula kay axiom number 1, 2, 3, and or 4. Kasi kung ganun din naman, wag mo na siyang isama sa axiom. Pwede mo na lang siyang tawaging isang theorem. Because the axiom should not be, these are statements needing no proof. Tapos gusto natin minimum nga yung number of axioms natin. So these are the 4 properties of an ideal axiomatic system. Dapat finitely describable. Kakaunti lang dapat yung mga basic axioms. Number 2, it must be consistent. Dapat walang contradictions, or these axioms must not contradict each other, or they should not result into contradictory statements. Number 3, it must be complete. Any statement in that mathematical system should be provable to be true or not. And then 4th, they must be independent. Dapat walang axiom ang pwedeng ma-derive from any other of the axioms. Okay? Now, here's an example. Siguro ito yung isa sa mga pinaka-basic na example, pinakamagandang example ng axiomatic system. This was in around 300 BC. Euclid already developed his geometry, which we know to be Euclidean geometry, using the axiomatic method. Kaya lang medyo meron pang ibang mga terms na ginamit si Euclid back in the day. Dun sa kanyang work na Elements, may tinawag siyang axioms, or kaya meron tong quotation marks. Hindi siya yung same axioms that I was referring to earlier. These are even more self-evident than the axioms na dinefine ko kanina. Pero ang tawag kasi sa kanya ni Euclid ay mga axioms. Pero siguro we can think of them as meta-axioms. Sila pa yung bago magkaroon ng axioms. Number 1, things are equal to the same thing are also equal to one another. Okay. So parang, paano natin to isa-summarize? I think this is the transitivity of equality. Pag si A ay equal kay B, tapos si B ay equal kay C, so ibig sabihin si A ay equal kay C. Okay? The second one, if equals are added to equals, then the wholes are equal. So ano naman to? Addition property of equality. Third, if equals are subtracted from equals, then the differences are equal. So parang restatement lang siya ng number 2. So ito ay A minus B equals, if A is equal to B, then A minus C is equal to B minus C. Number 4, things that coincide with one another are equal to one another. This is the reflexive property of equality. A is equal to A. Yun lang yung sinasabi niya. And then the last thing is the whole is greater than the part. So these are meta-axioms. These are the Euclidean meta-axioms, which are self-evident truths, and they are never proven. Okay. Yung example nung modern day axioms ay yung mga tinawag ni Euclid na postulates nung kanyang axiomatic system, yung kanyang axiomatic system for geometry. Okay? So ito yung sabi niya. Number one, it is possible to draw a straight line from point to any point. So basically, in modern language, it means that any straight line is determined by 2 points. Number two, to produce a finite straight line continuously in a straight line. So kung meron ka raw line segment, pwede mo siyang i-extend into a full line that extends in both directions. Number three, to describe a circle with any center and distance. So basically, it is saying that a circle is completely determined by its center and its radius. Number four, all right angles are equal to one another. And number five, which is the most controversial one, that if a straight line falling on two straight lines make the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. So ano daw ang sabi ng fifth postulate? The very statement of the fifth postulate led some mathematicians to believe that probably the fifth postulate is provable from the first four axioms or from the first four postulates. Kasi kung makikita niyo yung unang apat na postulates ni Euclid para sa Euclidean geometry, napaka-simple nung unang apat, right? Na hindi nga napuno yung isang line nitong document na to, right? So they are less than one line of this document. They are very simple statements. But look at the fifth postulate. Ang pagkaka-state niya ay parang isang theorem, right? So, ano bang sabi nito? In essence, if you have two straight lines, start ka raw ng sige, gawin ko to carefully. Kung meron ka raw dalawang straight lines, that fall on another straight line, okay? So ito yung another straight line na sinasabi ng theorem. Okay? And then the sum of the interior angles on one side is less than two right angles. Tama nga ba? Yun ang sabi niya. Okay. So ibig sabihin kung ito raw na angle na to at yung angle na to, ang sum ng measures ng dalawang angles na to ay less than dalawang right angles. Ibig sabihin that these two lines, the two black ones or black lines, when extended indefinitely, will meet in one point. So ibig sabihin niya lang, okay, pag in-extend ko to, sure ako na magmi-meet yung dalawa sa isang point doon on the same side of the plane containing the two angles whose sum is less than a 90 degree is less than two right angles. So basically the way it was stated and how it is illustrated, it seems that the fifth postulate is a theorem. And for hundreds of years, mathematicians tried to prove the fifth postulate from the first four. So anong property to ng axiomatic system na tinatry nilang i-prove na hindi nasa-satisfy nung postulates ni Euclid? Tatandaan niyo ba? Again, for hundreds of years, mathematicians tried to prove the fifth postulate from the first four. Kung nag-succeed sila, anong property ng axiomatic system yung na-violate ni Euclid? Anyone? Kung tandaan niyo yung mga pinagsasabi ko kanina. Oh yes, Victor?
Ano, sir? It should be independent.
Okay, thank you. That's right, Victor. Thank you, Esther. That's also right. The technical term is, tama si Victor, independence. Dapat hindi madiderive or mapuprove yung isang axiom from the other axioms. And this has been the dream of mathematicians. Hindi naman para i-criticize, para i-shame si Euclid. Nobody can shame Euclid. Euclid is one of the greatest mathematicians of all time. And the idea there is, gusto nila ipakita na hindi independent yung mga axioms ni Euclid, that the fifth postulate can be proven from the other four. And then throughout the years, tinry nilang i-analyze pa rin tong fifth postulate, and in 1795, John Playfair restated the fifth postulate in probably the more popular version that you might know. It says that in a plane, through a point, not on a given line, at most one line can be drawn that never meets the given line. So, ito yung tinatry kong i-describe kanina. Medyo sumabit yata ako ng konti. Pero what it says is that in a plane, and then you have a point, and then you have a given straight line. Okay, ito yung given straight line. Then the fifth postulate is logically equivalent to saying that there is at most one line that can be drawn through the point that never meets the given line. So, kaya ko raw mag-draw ng at most isang line na dadaan dun sa point na to na hindi mag-intersect dun sa red line. And basically, can say this is one such line, or almost. So, yeah. Oops. Yeah. So this brought about the notion of parallel lines, all right? So ibig sabihin, pag meron kang isang point at saka isang line, merong at most isang line na daraan dun sa given point na parallel dun sa given line. Yun yung sinasabi, or yun yung equivalent form ng fifth postulate. And even if in this with this simpler statement, para pa rin siyang theorem. Kahit naging mas simply na yung statement ng fifth postulate. That's why the fifth postulate was later known to be the parallel postulate, na laging merong isang parallel line na magpapass through sa isang given point. Okay. So, and then still, mathematicians tried to prove that the fifth postulate is not independent from the others. But the works of Fra Girolamo Saccheri proved that hindi, independent yung fifth postulate from the other axioms. And then, dahil na-prove niya na yung fifth postulate ay hindi, ay independent mula dun sa apat na axioms, it brought about some other mathematical discourses. So, naimbento yung mga non-Euclidean geometries. Once people accepted that the fifth postulate is independent from the first four, ginawa nung ibang mathematicians, pinaglaruan nila yung fifth postulate. Sabi nila, kung independent pala siya, pwede ko siyang baguhin, and probably I can create a different brand of geometry. And true enough, that's what we call now as the non-Euclidean geometries. For instance, we say, ang sinasabi kasi ng fifth postulate, there exists at most one line. Pero from the other axioms, mapapakita mo na merong isang line na nag-exist. So in conjunction with that implication, ibig sabihin there is exactly one line that can be drawn that never meets the given line. So sabi ng totality nung limang postulates ni Euclid, pag meron kang given line, given po at saka isang given point, meron lang isang parallel line dun sa given line na daraan dun sa given point. Pero sabi ng ibang mathematicians, bakit kailangan eksaktong isa lang? Anong mangyayari pagka pinalitan natin yung ikalimang axioms to the effect that there exists no parallel line? Ibig sabihin, kahit anong line pala, yung i-drawing ko mula passing through the given point, lagi pala siya daw mag-i-intersect dun sa red line. So if all lines meet, then kung yun yung ilalagay ko na fifth postulate, makaka-invento ako ng kakaibang geometry. And that's what we know as the Riemannian geometry, wherein walang parallel lines na nag-exist. All lines should meet at some point. Okay? Or, yung iba naman, ang ginawa nilang fifth postulate ay, kunwari, infinitely many yung parallel lines through a point to a given line. So naka-invento rin sila ng different brand of geometry called the Lobachevskian or the hyperbolic geometries, wherein there are infinitely many parallel lines. So depende kung yun yung effect ng pagbabago ng axioms. Nakadepende talaga yung mathematical discourse doon sa set of axioms na i-declare mo at the beginning. Okay? So, yun. it took about, let me just Google it quickly. Kailan nga ba na-prove yung fifth postulate? I think it was about in the 1800s, kung hindi ako nagkakamali. Yeah, it was only in 1733, I think, that uh, Girolamo Saccheri uh, prove that the fifth postulate is independent from the other four. So kung makikita nyo, it took about how many? About 1600 years in order for Euclid to be vindicated from every blemish. So yun yung they published it in the work in 17 nawala yung year, pero yeah, in the 1700s, that they were finally convinced that the fifth postulate is independent from the other postulates. So ito yung example ng isang axiomatic system na even though hindi pa modern times, dinevelop to ni Euclid, nagko-conform na rin siya dun sa notion natin kung ano yung ideal axiomatic system. Okay? Now, the next question is, okay, ito yung isang example. The next question is, can we attain an ideal mathematical system? So, yun nga, meron bang mathematical system that processes all these four ideal properties of an axiomatic system? And the answer was recently found in 1931 when Kurt Gödel, an Austrian mathematician, broke the dreams of Leibniz, Hilbert et al. Na sinabi niya imposible na ma-attain mo itong apat na properties ng isang axiomatic system. At least one of them must be given up. So, ibig sabihin, wala nag-exist na ideal mathematical system. Imposible na magkaroon tayo ng unified theory of everything or a unified calculus of reasoning that can describe all of mathematics. And this was contained in Kurt Gödel's Incompleteness Theorem, um, which was broached in around 1931. May dalawang statements yung Incompleteness Theorem ni Gödel. Unang sabi niya ay in any consistent formal system within a certain amount of arithmetic can be carried out, there are statements of the language of F which can neither be proved nor disproved in F. So kung meron ka raw isang consistent axiomatic system, merong mga statements na hindi natin kayang ma-prove to be true or false. And then second, may second part pa yung incompleteness theorem na sabi niya in such a consistent formal system, it is impossible to prove that that system is indeed consistent. Okay? So parang napaka earth-shattering yung discovery ni Gödel. Una, sinabi niya na pag meron kang consistent axiomatic system, hindi mo kayang ma-prove lahat ng mga statements. There are statements that cannot be proved to be true or false. And then yung second part niya, hindi mo daw kayang i-prove na yung system na yon ay consistent. Okay? Now, napakalaking discovery ito in the 1931s, which shattered years or hundreds of years of works of earlier mathematicians who are dreaming or actively seeking a unified theory for all of mathematics. Okay, and then siguro to understand more the incompleteness theorem, let's watch this video. I found this video from TED-Ed, which is a nice discussion about the incompleteness theorem. Let me just play this. For those watching the recording, baka ma-mute out ni YouTube ito. So if you want to watch it, bibigay ko yung link later. Or if you want, you can watch the recording in Microsoft Teams. Okay? So share ko lang share ko lang yung YouTube video. Nasaan na siya? Oops. Because I cannot discuss it better than this video. It's just 5 minutes long. So okay, please tell me kung walang sound. I hope share din yung audio.
Consider the following sentence. This statement is false. Is that true? If so, that would make this statement false. But if it's false, then the statement is true. By referring to itself directly, this statement creates an unresolvable paradox. So if it's not true and it's not false, what is it? This question might seem like a silly thought experiment, but in the early 20th century, it led Austrian logician Kurt Gödel to a discovery that would change mathematics forever. Gödel's discovery had to do with the limitations of mathematical proofs. A proof is a logical argument that demonstrates why a statement about numbers is true. The building blocks of these arguments are called axioms, undeniable statements about the numbers involved. Every system built on mathematics, from the most complex proof to basic arithmetic, is constructed from axioms. And if a statement about numbers is true, mathematicians should be able to confirm it with an axiomatic proof. Since ancient Greece, mathematicians used this system to prove or disprove mathematical claims with total certainty. But when Gödel entered the field, some newly uncovered logical paradoxes were threatening that certainty. Prominent mathematicians were eager to prove that mathematics had no contradictions. Gödel himself wasn't so sure, and he was even less confident that mathematics was the right tool to investigate this problem. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. A mathematical statement is simply true or false, but Gödel had an idea. First, he translated mathematical statements and equations into code numbers so that a complex mathematical idea could be expressed in a single number. This meant that mathematical statements written with those numbers were also expressing something about the encoded statements of mathematics. In this way, the coding allowed mathematics to talk about itself. Through this method, he was able to write "this statement cannot be proved" as an equation, creating the first self-referential mathematical statement. However, unlike the ambiguous sentence that inspired him, mathematical statements must be true or false. So, which is it? If it's false, that means the statement does have a proof. But if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement can't be false, and therefore, it must be true that this statement cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statements still are either true or false, but true statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove. Even if you account for these unprovable statements by adding them as new axioms to an enlarged mathematical system, that very process introduces new, unprovably true statements. No matter how many axioms you add, there will always be unprovably true statements in your system. It's Gödel's all the way down. This revelation rocked the foundations of the field, crushing those who dreamed that every mathematical claim would one day be proven or disproven. While most mathematicians accepted this new reality, some fervently debated it. Others still tried to ignore the newly uncovered hole in the heart of their field. But as more classical problems were proven to be unprovably true, some began to worry their life's work would be impossible to complete. Still, Gödel's theorem opened as many doors as it closed. Knowledge of unprovably true statements inspired key innovations in early computers. And today, some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. The Pythagorean theorem has more than 350 proofs. So what?
Okay, so that summarizes the Gödel's incompleteness theorem, and medyo napahapiawan nung video yung dalawang parts ng incompleteness theorem. The first part is if you have a consistent system, there would be for sure some statements in the logical discourse that cannot be proven using the axioms. And then second, we cannot prove that that system is consistent if indeed it is consistent. So hindi natin kayang ma-prove na yung axiomatic system natin ay consistent talaga. Okay? Which again broke the dreams of lots of mathematicians. And this is actually something that is a little bit hard to accept kasi gusto natin everything can be resolved in math. So there are some theorems that are there for hundreds of years, pero yun pala posibleng hindi pala natin siya ma-prove. A typical example is Goldbach's conjecture. Are you guys familiar with Goldbach's conjecture?
No, sir.
Yeah. Goldbach's conjecture is a very simple conjecture. It says that any number greater than 2, or let me just double check it a little bit. Baka mamali ako ng statement. Tapos bigla nyo pala siyang ma-prove, no? So this is one of the oldest and best known unsolved problems in number theory. And it says that every whole number greater than 2 is the sum of two prime numbers. So any number greater than 2 is a sum of two prime numbers. Is a sum of two prime numbers. So ito yung tinatawag na Goldbach conjecture. Kailan ba to? Let me see. When was it conjectured? It was conjectured in 1742. And for probably 200 years or so, some people are until now trying to prove the Goldbach conjecture kasi napakasimple ng statement, right? So kahit anong number na mas malaki daw kay 2 ay kaya mong isulat as the sum of two prime numbers. For instance, 3 can be written as teka, ano yung statement niya? Greater than 2. So ibig sabihin sorry, every even pala, any even number can be written as a sum of two prime numbers. Kaya natigilan ako kay 3, hindi ko siya kayang isulat as the sum of two primes. Pero any even number greater than 2 is a sum of two prime numbers. For instance, 4. 4 is 2 plus 2. 6 is 3 plus 3. All right, sum of prime numbers. 8 can be written as what? Anong mga prime numbers ang pwede kong i-add to get 8? I can have 3 and 5. And then for 10, I can have it as 5 plus 5. 12 can be 5 plus 7. 14 can be 7 plus 7, and so on. Okay? So ito yung Goldbach conjecture. Kaya daw natin itong gawin sa kahit anong even numbers. Pero until now, there is no proof of Goldbach's conjecture. To the point that some mathematicians believe that Goldbach conjecture is one of those unprovable statements using the formal construction of number theory. Tapos may mga iba pang problems. So you can Google out what are the Millennium Prize problems. Yung Millennium Prize problems are a bunch of mathematical problems or statements that are looking for proofs na pag na-prove nyo, you will win. Magkano na bang presyo sa Millennium Prize problems? Let me just Google it quickly. Okay, so So these are the Millennium problems which were proposed by actually by hold on, naglo-load yung search engine ko. But this is a problem that is proposed by the Clay Mathematics Institute in May 2000. And then I think there are 7 problems. And then yeah, and if you will be able to prove one of these problems, you'll win how much? Is it $1 million? Yeah, I forgot if it's 1 million or $2 million. So merong 7 problems na pinopose ang Clay Institute na to everyone. So kung gusto nyong tingnan, if try nyo, and you will win $1 million at least if you'll be able to prove if you'll be able to prove them. Out of the 7, only one was proven, and some people believe that most of the problems might fall under Gödel's incompleteness theorem. Okay. So yeah, with that note, I think we can end our discussion about axiomatic systems. Medyo historical lang yung development. Wala pa masyadong technical, and I think this is a good welcome back for us from the reading break. But next meeting, we'll start talking about technical stuff. We'll be talking about axiomatic set theory, which is basically the second half of the course. The course title is Logic and Set Theory. So next meeting, we'll start with the actual axiomatic treatment of set theory. And this is already in work in the second volume of the work text. So kindly download the second version, the second volume. And we'll be discussing pages 15 to 25, hopefully on Thursday. Okay? So para makausad tayo with the study guide. Okay? Any questions or concerns? Okay, so oh yes, Gat.
Sir, pwede po magpaiwan, may tatanong lang po.
Oh sure, yep. Okay, how about the others? Do you have some questions? Okay, so if not, yes, Victor.
Sir, so the incompleteness about the incompleteness theorem, it kind of feels like just like a bigger description of an axiom, if I'm right. Because it's just talking about how it can be either proven or not proven. Isn't that just like how an axiom is?
Uh, axioms are self-evident. So yung mga axioms, mga statements sila na hindi natin pinuprove. Sila yung serve as the building block, or actually not building block, but the foundation of any mathematical system. So sila yung mga statements na ginagawa nating assumptions. They do not need to be proven. Yung incompleteness theorem, isa siyang theorem kasi may proof siya. So hindi siya action. Na-prove to using logical arguments, okay? Now, ang medyo encompassing nga lang yung incompleteness theorem kasi pwede mo siyang isipin as a theorem that encompasses all mathematical systems. Yung axioms kasi, sila yung ginagamit natin para makaimbento ng isang brand ng math. Okay? Halimbawa, yung 5 axioms o yung 5 postulates ni Euclid, kung gagamitin natin siya sa axioms during the modern day, may imbento natin yung Euclidean geometry. So, yung 5 axioms na yun, hindi natin pinuprove. Inassume natin sila to be true. If you change one of those axioms, say the 5th postulate, you replace it by something else, then you will come across with a different brand of geometry. Yun yung mga non-Euclidean geometries na alam natin. So, specific yung mga axioms, okay? Kasi yung mga axioms, siya yung ginagamit natin para makaderive ng mga theorems. Pero yung incompleteness theorem, as the name implies, isa siyang specific theorem, which is proven. Ang problema nga lang or ang pinagkaiba ni incompleteness theorem sa ibang mga theorems na makikita natin or nakita natin ay yung incompleteness theorem, it encompasses not only a specific brand of mathematics but all types of mathematics. Actually, hindi nga lang sa mathematics, kahit anong formal system. Kasi ang sinasabi niya ay kung meron kang isang formal system consisting of axioms and statements, and it is for any such a system. Kapag ka siya ay consistent, may mga statement na hindi natin mapuprove. So basically, it is saying that if your axiomatic system is consistent, then it cannot be complete. Yun yung first part. So isa siyang theorem about the axioms. Pero siguro yun din yung sinasabi mo, Victor. Pero yun yung idea. Isa siyang theorem, pero isa siyang theorem about any axiomatic system. And perhaps it might be better next time if I will write down the actual statement of the incompleteness theorem. Sinimulan ko siyang isulat kanina habang nagve-video pero hindi ko natapos. Pero i-flash ko na lang siya next time, yung statement ng incompleteness theorem. But that's how it is. It is a theorem, but it is a theorem about axioms or any axiomatic system. Okay. Does that
Okay,
help,
sir.
Victor?
Yes, sir.
Okay.
Thank you, sir.
All right. Yes, Christian.
Hello, sir. Ayan.
Hi.
May hindi lang po ako na-gets. Sa
Uh-huh.
pag-prove po ba ni Gödel ng incompleteness theorem, parang gumamit siya ng isa pang axiomatic system?
Ang ginamit niya ay yung foundations ng logic mismo. Kasi idea niya ay pinuprove niya na kahit anong axiomatic system na consistent ay never magiging complete. Ang proof niya, ginamit niya ay yung axioms ng logical system. Pero hindi siya nakadepende sa isang specific na set of axioms for a brand of mathematics. So encompassing, he used concepts of formal logic. So hindi siya isang math, pero more of a logical theorem siya. So axioms of logic yung ginamit niya.
So, parang po, in our case, yung logical system na ginamit niya, yun yung arbitrary lang para ma-apply niya sa lahat ng axiomatic system?
Yes.
Okay po. Thank you, sir.
All right. Other questions? Okay, so if there are none, then thank you for coming today, guys. And then let's see each other again on Thursday. Bye, everyone. Oh, except Gad. Papaiwan daw si Gad.
Bye, sir. Thank you po.
All right.
Thank you, sir.